People have studied it for millennia, seeking to unlock its secrets. We've come a long way in our understanding, and in the process, we've uncovered a surprising truth. Everything that we see, the stars, planets, life, makes up only about 5% of the stuff in the universe. Roughly 25% is what we call dark matter, holding galaxies together through gravity. The last 70% is known as dark energy, accelerating the expansion of the universe.
Okay. So, if you'd argue that basically how the Big Bang formed was matter came from somewhere else and exploded into what we would define this little pocket of time and space, okay? Similar to like if you have a geyser under the surface of the water and at some point it explodes forth onto the surface and water starts bubbling up. However, if it then collapses back on itself and covers up probably the main part of where it first came out, however, you still have water trying to come up, then you'd have like other little pockets, other little geysers coming up, okay? And if there's enough force, well, then they keep going unless another object collapses back on itself and stops that little geyser from coming up. And then it would have to find a new little route coming up into our universe. Okay? So imagine that basically you have this geyser, it explodes up. Okay? You have all this energy, this Big Bang. Now at some point it shoots out far enough, expels enough, that the force driving it up is no longer greater than the mass right there. And then it collapses back on itself, thus creating a black hole. Kind of plugging that up. However, there's still more matter trying to escape into the universe. So you got these other little geysers trying to come up. Now, the one aspect you'd have to realize is the second one of these things shoots up, as long as that geyser's going off, you have incredible increases in time. So you have these little pockets in the universe in which mass time is traveling at a rate so much different than our own, in which you have like a vortex. Like if you're in the ocean and there was a giant typhoon or waterspout or whatever forcing water to be this little pocket in which, and instead of like, if it tried to like, anytime you tried to get near it, if it just like flung you away, it didn't suck you in, it just flung you away, type of a thing. You can never get stuck in this vortex because it's pushing outwards in your little world, okay? So this universe is water in this analogy. However, when things shoot up, it creates like this little vortex, it spins, and then if you get close enough to it, you couldn't penetrate it because it's acting out in different time. If you could even go into it, time would travel so fast that like you would age probably instantly. Anyway, if you could even go in there. Like 1 second would probably be billions of years or something, or millions, depending on, I don't know how. I don't know when the equilibrium probably happens. It probably happens when that accelerated time basically matches what we consider our time. So whenever these things collapse back and you can actually like go into them, they've probably now basically experienced the same level of time within these little dark matter pockets, you could say, as the entire universe. And so when those hit equilibrium, then you can probably go into them. Or when they're close to hitting equilibrium, then you can actually travel into these new pockets of newly formed universe. However, they would both seem, logically then, to be pretty much the same age. Meanwhile, the universe is still growing.
Building on Einstein's theory of general relativity, scientists have ideas about how dark matter and dark energy affect the universe, and they can test their predictions without knowing the identities of these mysterious substances.
The way that structures form in our universe is very sensitive to the proportions of and characteristics of dark matter and dark energy.
Okay, so once again, if you're viewing it as a geyser explodes into, every time it's plugged, it tries to explode back up into our universe, right? There is all this energy from the Big Bang. There's still more energy coming forth. Our universe is still growing, is still logically probably at an infant stage if you're seeing the acceleration this large. Meaning the universe is not even close to as big as its end result is going to get. So, that geyser still has a lot of energy. Just because you've plugged up one thing doesn't mean that there's not a force. And the second it explodes, then you keep expanding out. And so you have that initial force and pressure shooting forth, putting more pressure out, growing the universe. Until that geyser, explodes out, collapses in on itself. Once that new geyser basically collapses in on itself, that's when the pocket has the potential to actually be experienced in our universe at some time. Because as long as that geyser is shooting forth, time is going too fast. So that vortex is just ramping up, in which time is just going wild. And not until it collapses in on itself, creates a black hole, can it ever get to equilibrium into our existence.
Without a certain amount of dark matter, there wouldn't have been enough mass in the early stages of the universe to form structures like galaxies that are very comfortable hosts that we live in. But without a specific percentage of dark energy, there might have been too much structure. So we need a very precise balance to be able to make the universe that we observe.
There seem to be some interesting tensions between observations that we've made of the early light in the universe, like the cosmic microwave background, and observations that we make of the local universe, so what's really near to us. We have a hint, however, that the local measurements give slightly different values. So the question is that real?
Now, new results from the Dark Energy Survey take us one step closer to figuring out how the universe got to be the way it is, and what the future has in store.
The Dark Energy Survey is an international collaboration that aims at observing hundreds of millions of galaxies and taking pictures of them.
The primary science goal of the project is to study the distribution of galaxies in space, and that helps us.
The biggest question is, if this is all acting out, and our universe has an edge, right? What happens if the edge of our universe actually is a geyser trying to reach equilibrium, meaning our time is going faster than something on the edge, which once it hits equilibrium, we open up to possibly a larger universe, which would be a far cooler aspect.
Let's better understand the expansion of the universe, and that's related to dark energy.
And then if you really want the Star Trek thing, that what we would open up to would be where vast levels of alien life would be.
The multinational project led by Fermilab is based at the National Science Foundation's Blanco Telescope at Cerro Tololo Inter-American Observatory in Chile. Over more than 300 nights, the survey charted about 1/8 of the whole sky and includes the largest sample of galaxies ever used for cosmology, over 226 million of them.
The lens of the dark energy camera is more than 3 feet, and it can take pictures with a whopping 570 megapixels. This is far beyond the capabilities of our iPhone, which takes at most 12
In the Dark Energy Survey, we use several probes, but the most powerful of them are galaxy clustering and Buick gravitational lensing.
They exist in a web, and that's what we observe. We observe this web.
And more clustered galaxies allude to more dark matter in that region. So the galaxies serve to illuminate the dark matter scaffolding.
Weak gravitational lensing, it's a name for an effect that we can use to help understand dark matter and dark energy. I have a wine glass here, and the wine glass bends the light that passes through it. If I put like the base of this wine glass on the camera, you see that the image is going to be distorted. And importantly, that as I move the wine glass away, you see the amount of distortion changes, and that's exactly what we're studying with the Dark Energy Survey.
Figuring out those patterns is a complicated process. It's a bit like looking at an abstract painting and figuring out the order in which the layers were painted.
To do weak lensing and clustering, we need to understand how far away the galaxies are, so the distances from Earth to the galaxies. And we call this the redshift. So the higher a redshift a galaxy has, the further away it is from us.
So redshift refers to the change in the color of light. So light has been shifted to be more red. When a galaxy is moving towards you, it would appear bluer for this reason, and when it's moving away from you, it appears redder. Redshift then is a measure of the velocity of an object relative to...
Okay, so if you picture a geyser, redshift would tell you probably where you're having more pressure, right? The darker the shift, the more pressure you're having go forth. So the other thing you have to realize is for a white hole to basically come up, you gotta push away our universe, create like this little bubble, explodes forth. It creates its own time space that's acting out as long as that dark matter is basically coming forth in our universe at an incredibly crazy rate. And then at some point it mellows out, most likely when time would match our time, it dissipates out and we can view it. Okay? So this is the one thing. It would not look like, once this all disappears, it would just look like something that's been there for the same level of time as we have. It could be a completely newly formed universe. No clue how long this takes. Because time's acting out who knows how fast in there. I mean, granted, the larger these pockets are, the faster this happens. And some of these universes could be being churned out, as in, like, the guy just shoots out and somehow a little piece gets pushed further out and becomes its own little pocket. So then you could have these little pieces, like these little universes, outside the major geyser, possibly, of the dark matter, getting kind of shoon out. And so these ones have reached equilibrium with us, so then they look like they're part of us, but their source would still be there. If it was like a vortex coming forth in the water, things within that vortex could actually be churned out of it. Type of a concept.
In the Dark Energy Survey, we make photometric observations. So we observe each galaxy in different filters on our camera, and that allows us to pick up different features and measure the colors of these galaxies, which we use to determine their distances.
We need to measure how far these are with extreme precision, otherwise we can get biased results and then won't matter.
The Dark Energy Survey gives us a clearer picture of our universe than ever before. The results of our analysis are as impressive as the road to get there. We found that our measurements are well described by predictions that we make from the Standard Model of Cosmology. Measurements of the early universe are an exquisite fit to this model, but they probe the universe at an unrecognizable stage, when it's just a plasma of particles. Very different to the one that we observe with the Dark Energy Survey, which is teeming with galaxies and dark energy.
So it's a beautiful test and a remarkable feat that one theory can describe billions of years of cosmic evolution. Now, our analysis best measures how clumpy the matter in the universe is. And it is intriguing that our measurements find slightly less clumpiness than what the early universe dictates. So although our standard model survives...
Okay, so there's slightly less clumpiness than the early universe predicts. Well, if you had a geyser come forth, shoot forth, or vortex, or however you want to view this, if you view basically the Big Bang as a geyser coming forth, okay, and it shoots up. However, it shot up all this pressure in this analogy. So the geyser shoots up. When the pressure of the geyser isn't enough to keep like a giant rock that's floating on top from staying there, that rock can then collapse back, plug it up. So you still have all that stuff still trying to come into our time space, but it's initially plugged. And so now it's got to burrow itself around that plug. So the early universe shot forth, its source collapsed in on itself, creating a giant black hole. However, the force, it just plugged that one. So that there's still matter trying to come up.
a more stringent test than ever before, there is enough ambiguity to keep us looking up. Now, the Dark Energy Survey has double the amount of data still to be analyzed. So we're really just at the beginning of learning what we can from the darkness, and that's exciting.
The Dark Energy Survey has already done a lot of great science. Now.
All right. Have a good one. Thanks for listening. Bye.